Welcome to the chapter on mathematics for chemical engineers. Mathematics is a fundamental tool for chemical engineers, helping in modeling, analyzing, and solving engineering problems. This chapter covers essential mathematical concepts crucial for first-year chemical engineering students. In this chapter, we will cover solving equations, differential equations, and the basics of statistics and probability. Chemical engineers often need to solve various types of equations to model chemical processes. These equations can be algebraic, linear, or nonlinear. An algebraic equation involves only algebraic expressions. For example, the equation for the equilibrium constant K in a chemical reaction is given by K equals the concentration of C raised to the power of C times the concentration of D raised to the power of D, divided by the concentration of A raised to the power of A times the concentration of B raised to the power of B. Linear equations are first-order equations. They can be written in the form ax plus b equals 0, where a and b are constants. For example, the rate of a first-order reaction can be described by the linear equation dA over dt equals negative k times a, where a is the concentration of the reactant and k is the rate constant. Nonlinear equations involve terms that are not linear. For example, the van der Waals equation for real gases is a nonlinear equation given by the formula P plus A over V squared times V minus B equals RT, where P is the pressure, V is the volume, R is the gas constant, T is the temperature, and A and B are constants specific to the gas. Differential equations involve derivatives of a function and are used to model dynamic systems and processes in chemical engineering. An ordinary differential equation involves functions of a single variable and their derivatives. For example, the rate of change of concentration in a batch reactor can be described by the ODE, dC over dt equals negative Kc, where C is the concentration and K is the rate constant. Partial differential equations involve functions of multiple variables and their partial derivatives. For example, the heat conduction in a rod can be described by the PDE, partial T over partial T equals alpha times partial squared T over partial x squared, where T is the temperature, T is time, x is the position along the rod, and alpha is the thermal diffusivity. Statistics and probability are essential for analyzing experimental data and making informed decisions in chemical engineering. Descriptive statistics summarize and describe the main features of a dataset. Key measures include the mean, represented by mu, the median, and the standard deviation, represented by sigma. For example, if we have the following dataset of reaction times in seconds, 2.1, 2.3, 2.5, 2.7, and 2.9, the mean reaction time is calculated as the sum of these values divided by 5, which equals 2.5 seconds. Probability is the measure of the likelihood of an event occurring. For example, the probability of drawing a red ball from a bag containing 3 red balls and 2 blue balls is calculated as the number of red balls divided by the total number of balls, which equals 3 over 5, or 0.6. Probability distributions describe how the probabilities of a random variable are distributed. Common distributions include the normal distribution, which describes data clustering around a mean, and the binomial distribution, which describes the number of successes in a fixed number of independent Bernoulli trials. For example, the probability of getting exactly 3 heads in 5 coin flips, where the probability of heads is 0.5, can be calculated using the binomial distribution formula, which equals approximately 0.3125. Understanding these mathematical concepts is crucial for solving real-world chemical engineering problems. By mastering these topics, you will be well equipped to tackle more advanced subjects in your studies.